Okay, and all distinguished participants in this international workshop. Yeah, as I already mentioned before, today is the fifth meeting of international workshop in building with nature as the last meeting in this workshop. So actually, we already have the first meeting in introduction of building with nature, and then the second discussion on pro and cons of building with nature projects, and then the third meeting was this case study of civil work and also cultural work, and then the last week meeting we invite one of public person in East Java giving explanation and sharing experience in implementing building with nature in river work in East Java, Mr. Fauzi, and also Helen and I forgot, and Michelle from both and with of him joined with us in the last meeting. And then, okay, because today will be our last meetings in international workshops, so jump to our main agenda today. I would like to invite Pak Boke for delivering closing speech because I know that Pak Boke has a meeting in the middle of our workshop. Pak Boke, time is yours.
Matur nuwun, Pak Bambang. Thank you, terima kasih untuk semua. It's my honor to have this closing speech, and I think it's an honor not really belonging to me. I think I'm representing here Amrit, who is much more knowledgeable about building with nature than I am. But I'm happy to represent him and also the rest of Deltares. And what pleases me so much is that when I think back of 2 years ago, almost 2 years ago, when several of you participated in the training of trainers on building with nature, and we signed this memorandum of understanding, no, memorandum of agreement, in which we pledged to cooperate and to do what we can to further the building with nature in Indonesia. I could not have thought that actually we would have this workshop. So I really want to congratulate Brawijaya University and Pak Bambang and his team for having organized this workshop. And I think it was very useful. And I think for my part, it was very interesting also to hear the questions and hear the remarks and to hear the experience that already is present among the participants, but also the eagerness to learn new things. And I hope you can apply those new things. And one of the things that, of course, we hoped for during the training of trainers in Bali, almost 2 years ago, is that you would see ways to include building with nature in your existing curricula, in your existing courses. And of course, I would love to hear maybe later to what extent you are able to do that and to what extent you need extra information or extra help from us or from Wetlands International or from Witteveen en Bos or from any other angle of this world that has experience with building with nature. As for now, I'm really happy, and I'm happy that Deltares could play a small role in this excellent workshop. And I think we haven't completely fulfilled our role yet because Bob is still to give his contribution. And I'm sure that will be a very relevant and useful contribution. So maybe it's best that I stop talking now. Thank you again very much. Matur nuwun. Pisan. I don't know whether that's Japanese. I think that's Sundanese. Pisan.
Okay, that one is Japanese, I think. Matur nuwun pisan, isn't it?
Matur nuwun pisan. Okay.
Okay.
Matur nuwun naker. Oh, that's another one.
Okay. Okay.
Thank you very much.
And, for your closing speech. Okay. Now we are going to the next agenda. Presentation by Bob Smith. As I already mentioned before, today workshop will be the one and only speakers. And then no, I would like to invite Bob for delivering his presentation. Bob, time is yours.
Thank you very much. And thank you for inviting me to present to you today. I will share my screen. Let me see. So, can you see my screen?
Yeah. We can see your screen clearly.
Okay, thank you. So I will be presenting some work that we did with the Deltares team together with EcoShape and Wetlands International on the Muck mangrove mud coast. I'm actually not completely sure where you are located yourself. So the Muck you are probably familiar with, but it's located on the north coast of central Java. This is an area that we've been involved in for a longer period. And I will briefly tell you a bit about the project itself, and then I will zoom in on the modeling aspect that we did in this project. The slides I'm using today are slides that I also presented recently at an international conference, which has a bit more academic focus. So the focus of the presentation is slightly towards, well, whether we can help the Demak mangrove mud coast to keep up with relative sea level rise. I will also tell you a bit more about the project, but the focus is more, let's say, somewhat more generic to see whether such a coast can keep up with relative sea level rise. So to introduce first the scope of this work. It was the work was part of a project funded by ICI, which is an international climate fund. It was about this mangrove mud coast in Demak, where there has been heavy erosion throughout several decades. You can see the figure on the right shows you different coastlines, different colors indicate different years. So the oldest one is the black line, which is furthest out towards the northwest. So on the northwest, the top left angle of this figure, you see the sea, and on the right hand side you see the land. And the black line is the old coastline of 2003, which was well, almost a straight coastline. And the newest or most recent one in this figure is from 2013, which is the purple line. And you can see that it retreated all the way back towards the village of Bogorame. And this is about, well, at some locations up to 1 kilometer or several hundreds of meters further backwards. So there's been a lot of coastal erosion. And this has mainly been caused by mangrove removal and land subsidence. Mangroves have been removed mostly to apply aquaculture ponds. And land subsidence is mainly caused by groundwater extraction, some by some of the local inhabitants, but mostly by the larger industries. Also near Semarang, the city that's located close by. So what the EcoShape consortium did is implementing permeable structures, such as the one you can see on the bottom right, to restore the sediment balance and to promote the natural recruitment of mangroves. And I explicitly state it as such because we've not been planting mangroves, but we've really tried to let the mangroves regrow from a natural process perspective. So without planting, making sure that the physical conditions are right for mangroves to grow. So within the modeling part of the project, we've tried to assess the effectiveness of those permeable dams under different scenarios of sea level rise and land subsidence, by simulating the development of the coastal area. And I put there the morphodynamic development. So that's let's say the processes involved in hydrodynamics and in sediments to create and to alter the bed levels in the environment. The research question I will focus on in the presentation is, can we help this mangrove mudcoast to keep up with relative sea level rise? And so for this ICI project, there were different tasks to put a bit of perspective for the larger project. We've been involved in the design of those dams. We've been involved in monitoring of bed level changes and of mangroves. There's this modeling task, which I will be focusing on right now today. But we've also been involved in training sessions. We've been involved in upscaling for other locations along the Indonesian coastline, but also other areas in Southeast Asia. And things like a vulnerability analysis, freshwater management. So there are different aspects that we've been involved in, and today I will pick out only the modeling task. Well, this shows you a bit more where this location is. I'm sure you are well aware, probably more than I am, but just to give you an indication and to tell you a little bit about this natural system, this coastal area. You can see an aerial figure on the right hand side. And historically, mangroves have always protected this coast from erosion and from flooding. And as I mentioned before, if we want to have natural mangrove regrowth, we first need to make sure that we have the right physical conditions. And in this case, that means we need to restore the sediment balance. We need to make sure that there's not only sediment being taken away, eroding, but there's also sediment supply, and enough sediments are kept within the coastal zone. To do that, we decided to use those permeable dams. Further, this coast is characterized by a muddy environment. So the substrate or the sediments are very muddy, cohesive sediments, which tend to have mild slopes. So it's not a steep sloping coast, but it's quite mild sloping coast. And there are channels in front of the coast. And channels are sandy, consist of sandy material. And those sand layers are sort of sand lances that are on top of the muddy substrate. So it's a sort of small sandbar which is located on top of the muddy substrate. The dynamics of those sediments are mainly driven by tides and by waves. And what we tend to say is the waves, they mobilize the sediments, they bring sediments in suspension, and then currents mix those and transport them towards the shore. So to give you some figures about those tides, the tidal signal is diurnal. So that's one high water and one low water per day mainly, with a small semi-diurnal component. The amplitude is about 40 to 60 centimeters, and the tidal current velocities are rather small. And further, the environment is, of course, characterized by a monsoon. So there is a northwestern monsoon season, which is between November and April, and this is typically known as the wet season. So maybe people know this as the monsoon season, but it's one of the two seasons. The wet season is from November to April, and the wind speeds are about 4.4 meters per second, medium wind speed, and the waves are offshore up to 0.7 meters. And the winds are directed towards the coast, which makes the coast more exposed to waves and impacts of waves. During the other half of the year, there's the southeast monsoon from May to October. The winds are the wind speed is not as large, and the waves are also a bit smaller. And because the winds are directed offshore, the coast is less exposed, a bit more protected. You can see typical wind roses for January and wave rose for January on the bottom right. Towards climate change and long-term scenarios, we look at sea level rise and we look at land subsidence. So we made three scenarios here: a best case, a mid case, and a worst case. And you can first see the number for the sea level rise rate that we implemented. This is based on the IPCC report of 2014. So that's not the latest one, but one before, because we did the work a few years ago. And the differences are not so large. The rate of sea level rise would be between 40 to 60 centimeters per year, 0.4 to 0.6 centimeters per year. So the differences are not so large, but when you compare this to the land subsidence rates, you can immediately see that there's a large difference there. So the land subsidence is a lot larger than the sea level rise. And the rates that we included are between about 8 centimeters per year up to 13 centimeters per year. The time scale we looked at is up to 10 years. So if you look at a 10-year difference, the total amount of what we call relative sea level rise, so that is adding up the sea level rise itself, the absolute sea level rise, and the land subsidence. So if you would add that up over 10 years, you end up with 80 centimeters up to 1.4 meters about. So that's a lot, and that's very large rates of relative sea level rise, much larger than we see anywhere across the world. So that's why this is a very it's a very devastating example, but it's also from a scientific point of view a very interesting example to look at, because it can tell us a lot for other areas in the world. So just to stress it even more, the land subsidence rate is about 20 times as large as the sea level rise. And this is not a natural phenomenon. So the land subsidence is really caused here by groundwater extraction, and that's mainly due to the extraction by the industries. You can see on the bottom right, you can see also a figure of the land subsidence, and you can see on 3 different locations where it was measured. And it's really close to Semarang. The largest rates are monitored, actually, are found. And well, so as I maybe already mentioned, some motivations for this research is it's really extreme land subsidence rates here can really be an example also of sea level rise that we can expect not within 10 years, but within longer timescales elsewhere across the world. And this area could really be interesting from that scientific point of view to really understand how this works and what effects it would have on the coastal response. So towards methodology and a model setup, I'll briefly go through this and we can discuss it more if you have questions. That's perfectly fine, but just to give you an outline. When you start modeling, you always need to make some simplifications and to make some assumptions. You can never capture everything within one model. So you need to make some decisions. What we decided here is to go for a 2D model. I call it 2DH because we do a horizontal model in 2D with hydrodynamics and morphodynamics in it. And we use the tool Del3D Flexible Mesh, which is a Deltares model. It's open source, so anybody can use it, and it's relatively new. I included in the model this relative sea level rise, which includes the sea level rise itself, the absolute sea level rise, and also the land subsidence. But what I did is I schematized it only as a sea level rise on the seaward boundary. So I did not do any land subsidence in particular, but I just assumed it to be an increase in the water level. We did not include the vegetation itself, so the mangroves are not included. So any feedbacks the mangroves would have on hydrodynamics, on waves, on sediments are not included in the model. That's a pity, but we needed to make some decisions. We couldn't do everything. We did include those structures, the permeable structures I showed you the figure of, by having dissipating elements, energy dissipating elements in the wave module, and also having, well, in this case, impermeable, but some structures also in the flow and sediment modules. Impermeable only because we didn't have an option to do it with the permeable structures. We used impermeable structures there. And then we set up the sediment model as what we call a local sediment redistribution model. And I will show you in the upcoming slides what I mean by that. Then we simulated the bed developments during the northwest monsoon season only. And that's because we've seen in observations that outside of the northwest monsoon season, the bed level changes are not so large. So we assumed that the main bed level developments would occur during this northwest monsoon season when the coast is more exposed. So that means that we only needed to simulate 3 months per year instead of simulating 12 months per year. So that saves us a bit of computation time. So to show you the domain, I hope you recognize this coast a bit. So this is the north coast of Java, and Semarang is located about here. I hope you can see my mouse. And then where you see those eyes and those pink stripes, this is really the project site where the Demak district is located. So Demak itself is a village somewhat more inland, but the coastal area here is what we've been focusing on. And the boundaries that we used are offshore, tidal water level boundaries, and also wave boundaries. And you can also see that we've been using this flexible mesh in the sense that the computational grid itself is also unstructured, and it has different cell sizes. So further offshore, we have larger cell sizes of about, I think, 500 meters. And near shore, really at the coastline, we have cells of about 16 meters. So there's a large difference in the cell size, which makes it computationally more efficient. Some boundaries and model settings. So we use tidal water level boundaries. We use spatially uniform winds, but they vary over time. So they don't vary over the grid, but in time they do vary. So there's the seasonality in there. We use the Swan wave model and sediment model with two cohesive sediment fractions for which the Parteniades equations for erosion and deposition are used. So that's specifically for cohesive sediments. And there's no suspended sediment inflow at the boundaries. And that's also why I said a local sediment redistribution model, because we only use the sediments that are already within the domain. And those sediments are being mobilized and redistributed within the domain. So some parameter settings to give you an idea. The winds are between 3.5 and 8 meters per second. So with the seasonal signal in between. And the waves between 0.4 meters and 1 meter wave height, and then wave periods of about 5 seconds. And sediment parameters, well, I've put there. I'm not sure if you're familiar with these abbreviations, else we can talk about them maybe after the presentation if you have questions. So always, if you model, you always need to also explain how your model is behaving and what you understand from this. Why would your model be right? So that's what we call validation. And I've put it here between parentheses with a question mark, because, well, it's quite hard to do a proper model validation in this area because there's very little data available. What we did do, we checked the current velocities and the circulation patterns, and we compared them to literature, which is in this case Ritke, and actually it compares quite well. The winds seem to drive the main circulation patterns, which is longshore directed, and then the tide governs the local current direction. So if you zoom in, the cross-shore tidal exchanges or the cross-shore currents are really governed by the tides. Then we did a verification of the wave transformation. We did have a wave buoy from a PhD research project. When we check their results, we see that we capture part of the measurements. So the blue line here shows you the measurements. If I sort all the recorded values from the lowest to the highest value, and I also sort my modeled, my simulated outcomes, then we see that we capture only a part of this. The part that we do not capture, the lowest waves, anything before, let's say the lowest 1/3 of the waves, 33%, we are not so worried about because that's not the part that we are interested in. But we're also missing the 20% largest waves. So maybe we are missing something there, but we think this is acceptable to say that we want to look at the long term. We are not interested in the very short term dynamics, but mainly looking at the long term, we see that, let's say, the representative daily conditions are included in there. So a large part of the spectrum is included. But maybe, yeah, we may be missing something. And I think that can be acceptable because of the way the bed shear stress has been formulated. This goes very much into detail. So I'll leave it at that for now. And also because we are missing some of the wave dissipation factors that may be influencing here. So that would be the wave dissipation by fluid mud. And therefore we think it's okay to work with slightly lower waves than in reality. And then the sediment dynamics, we couldn't really compare it with any data. The only thing we had was some short-term accretion rates in the intertidal area, and it compared quite well on that data. But for the long term, we could only use some expert judgment based on our experience in other projects and elsewhere, and some of my senior colleagues. this is the best settings we could come up with. There was simply no other data available. So yeah, the validation, as I call it, it's maybe a bit poor, but this is what we could do within the constraints of this project and within the time and budget. So some of the results, so the highlights. I want to stress that the model is really a tool that we use to gain more insight into the behavior of this coastline for different scenarios of relative sea level rise, and that we want to use it to study the effectiveness of those permeable structures. So that means that we don't need to have the perfect outcomes for example, the bed level change or the water level or the current velocity, but we need to have a good enough estimate to be able to compare when we implement structures and when we leave the structures out, what the difference would be. It gives us an indication of some trends and developments, and it can give us some help if we look at relative quantities. So if we do not look at the absolute numbers, but if we look at the change in, for example, current velocity or the change in a bed level accretion. So showing you on a, let's say, aggregated level, if you would think of this figure on the top, you see, let's say the water depth H there, and there's always an increase in the water level, the blue arrow, because of the relative sea level rise. And then there could be either accretion on the bed, the green arrow, or there could be erosion on the bed, the red arrow. And so the figures I'm showing you now here are for the three different scenarios. First, an autonomous development, so that is without implementing any structures, and then the results with the permeable structures. So these negative numbers, the minus 0.44, minus 0.45, those are erosion rates. So those are the red arrows, the bed is going down if we do not protect the coast with any additional measures. And then if we would put the permeable structures there, you can see that there is accretion by between 0.34 to 0.44, in this case meters. So that's about 44 centimeters, 34 centimeters. And so the difference between with and without dams is about, let's say, 80 to 90 centimeters difference. That means that we do make a big difference. And you can see indeed that the permeable structures have a positive influence, but also you see that the green arrow will not be as large as the blue arrow is. So the increase in the water level, for example, here for the best case is 80 centimeters, but the accretion rate is not 80 centimeters, it's less than that. So our water depth will increase. I hope that that story makes any sense. So yeah, as I put now also on the left, there is accretion behind the structures, 30 to 40 centimeters. And with the higher rates of sea level rise, we see more accretion, but it's not enough to keep pace with the sea level rise rate. But that's not the whole story. So this is only if we look at the very end, and if we combine all our structures together and look at one typical structure. But if you look at the time variation, this is the figure that we would get. And what you see in those figures is for the three different panels or the different scenarios, and you see in blue, you see the water level, and the water level is increasing over time because of the sea level rise. And you also see the tidal variation in there. So you see spring neap cycles. And then you see two lines, one black line and one red line. The red line is what would happen if we do not include any structures. So if it's autonomous development, and the black line is if we include those permeable dams. And what you see happening is, for example, if I focus first on the best case, you see that without any structures, for some time, there is some accretion on the bed. So the red line is increasing until year 5, I would say. And then you see a lot of erosion happening. And if you do include the structures, you see that the bed level is increasing, and it keeps on increasing for about, I would say, 7 years. But the last 3 years, it remains pretty much stable. So it cannot keep up all the way, but for the first 7 years, it seems to keep pace. Well, for the other scenarios, you see something similar going on, but the deviation occurs earlier. So for the intermediate case, I would say the black line can follow the sea level rise for about 6 years. And for the worst case, you can see that the black line follows the sea level rise for about 5 years. But after that, it cannot keep pace anymore. Hope that makes any sense. So between 5 and 7 years, we can keep up with the sea level rise rate depending on the scenario. And it seems that once a certain threshold amount of sea level rise has been exceeded, the bed cannot keep up with sea level rise anymore. And this is due to a positive feedback mechanism, because if the water depth starts to increase, the waves become higher and the bed shear stresses also increase, which causes erosion. And because of the erosion, the water depths increase again, and we go back in this cycle, and it keeps on continuing in a negative direction. So to show you also some spatial plots, what you see in this figure is the coastline really zoomed in, and so on the left-hand side of the figure there is the sea, and on the right-hand side there's the land, and this black line here shows you the coastline, the previous old coastline, and the colors in this figure indicate the bed level change. So any blue colors are erosion, any yellow, orange, brown colors are accretion. And I included a special part of the color bar, which is green, for any areas that are growing at a rate faster than the sea level rise. Well, as you can see, there are no areas that are green, so there is no area where it grows faster than the sea level rise. But what you can also see on the left-hand side, the autonomous, on the right-hand side, the structures. If we would put structures, you see that there are those orange and brown areas popping up behind the structures. So there is really an effect noticeable of the structures. There's really sediment accretion behind the structures. So that's quite nice. So some discussion, and then I'm going to wrap up. Some interpretation of these results. Please keep in mind that the results are really only representative for situations in which the structures are well maintained. So that's really an idealized case. In reality, we often see that the structures are damaged by a storm, or they are not maintained well, and then they will not perform as they do in the model, because in the model they are always perfectly maintained. Then a first finding would be that the structures do help. They capture sediments for all of the scenarios. And for some years, indeed, the bed seems to keep pace with sea level rise, even though there are very extreme land subsidence rates, but still they seem for a certain number of years to keep up. But after 10 years, in all 3 scenarios, they cannot keep up anymore, and the coast starts to drown, really partial drowning of the coast, because we can compensate for part of the sea level rise, but not for the entire amount of sea level rise. And there seems to be a sort of threshold behavior. So after a certain amount of sea level rise has been surpassed, it cannot keep pace anymore. And this seems to have something to do with our exact choice and definition of some of the sediment parameters. So specifically the critical shear stress for erosion. If we would change that a little, we would get a different number of years. But in all cases, whichever value we choose, we do not get 10 years. So we cannot keep pace for all the 10 years. So there are also some things in the method that you could question or that you could discuss. For example, we decided to simplify some of the processes. We did not include 3D effects. We did not include the mangroves. The land subsidence was implemented as a spatially uniform thing, whereas in reality, it's spatially varying. So there would, of course, be ways to improve this. There are also some limitations in the software, some things we simply couldn't do because the software is not able of doing that. And there are also some new findings and hypotheses after we've finished this work and reported it. So there are still things to update. And maybe last but not least, the sediment source. We decided to really look at the sediment, local redistribution of the sediment. So that's really the seabed in front of the coast, but we're not really taking into account any outflow of rivers or other sediment sources. And what's also interesting is to look at this graph, and maybe that goes a bit into detail, but for more academic purposes, it could be interesting to look at the balance between, on the vertical axis, the rate of deposition, and on the horizontal axis, the relative sea level. And so if the sea level is rising rapidly, we are on the right-hand side of this graph. And if there is a lot of sediment available, we would be on the lower part of this graph. But if there is not so much sediment available, we are in the top part of the graph. So you could look into this a bit more and play around with how much sediment is available and how much sea level rise do you have, to look at, to try, if you want to translate this result to other areas around the world. It would be interesting to see if an area has much more sediment available, where would it be on this graph? If an area has much less sea level rise, where would it be on the graph? And then you can try to translate those results from one particular area to other locations. So that's why I included this picture. So to finish off with conclusions and recommendations, coming back to my research question, can we help the Damak mangrove mud coast to keep up with relative sea level rise? The conclusions here would be, well, without doing anything, the coastal zone of the Damak will certainly drown, and there will be loss of coastal areas. If we try to help them and implement those permeable structures, we may be mitigating some of the effects. And we show with these model simulations that we can locally stimulate the sediment accretion, and we can help the bed level to keep up for part of the time. But in the end, the structures can only limit and postpone the drowning. But with these extreme subsidence rates, as we see in the Damak, it's not possible to protect the coastline entirely from drowning. Some recommendations for further study. It could be interesting to use this case, as I said, to also study other areas, and specifically for the Damak. It's really worthwhile to look into how we can minimize the amount of relative sea level rise rate, and the one that we have the most influence on would be the land subsidence. So if you would stop with the groundwater extraction, we can really limit the amount of sea level rise and thereby prevent all this drowning from happening. So I hope these figures have been quite maybe scary also to see because of all the flooding that will be going on. I hope that will not happen, and we can prevent this from happening by stopping the land subsidence mainly. So with that, I would like to thank you for your attention. Terima kasih. And I'm happy to answer some questions and to discuss this with you.
Okay, terima kasih Bob. Thank you very much, Bob, for your interesting presentation. We are open for Q&A session. If you have any questions, you can ask directly to Bob. Okay, while we are waiting for question from other participants, in your analysis, in that location there is a permeable structures. And then your model that you use is using 2DH approach. And then when we talk about 2DH approach, mean that the velocity is using average velocity in the vertical directions. And then how to compute about permeable structure and the velocity distribution, especially in average velocity. Because as long as I know that the permeable structure in the map, I mean, the water is still can pass that structures. And then the water of, pass in that structure is not only in the middle of the structure, but also could be in the bottom one, could be above of in the middle ones. So how the model can cope that kind of phenomena? Yeah, thank you for the question. So indeed, the model is only 2D. So that means that the vertical velocity, or let's say the velocity profile is only using one depth average velocity. So we do not have the exact vertical profile of the velocity, in which the velocity would be a bit larger, maybe on the top near the water level, and a bit smaller on the bottom. But we're just using one depth average velocity. That's a simplification we think is safe to make, because the differences will not be that large. And the main reasons for having 3D models and 3D effects is if you would want to, for example, model density differences, where salinity differences play an important role, or where the sediment concentration is so large that they start to influence the density of the fluid. And that's not really the case in this area, so we think it's safe to assume this. If you would really look closely at a small scale near those structures,
then it may be better indeed to have it also in 3D. But you should both have the model and the fluid mechanics in 3D, but also the structure itself should be in 3D. And in this case, we also couldn't implement the structure itself in 3D, so it doesn't make sense to make your model very complicated if the structure you are simulating is very, very simple. It's even this simple, as I mentioned in one of my slides, that the permeability of the structure could not be implemented in the model. And that's a bit of a, let's say, a lacking thing in this model. But that's simply because the software at the time was not able to implement permeable structures. So what we did is we made the resolution of the model, the cell size, well, the resolution so high or the cell size so small that the water is able to pass the structure sideways. So in a horizontal plane, the water can go around the structure, but it cannot pass through the structure simply because we close off the side of the cell, because that's the only way that the structures could be included in this model. So it's not the best possible option there is, but it's what we could do here.
Okay, thanks, Bob. I got the point that in your analysis, you assume that there is no water passing that structure, isn't it?
Yes.
So the water can move around the structure, but cannot pass that structure.
Yes.
Yeah. Is there any question from other participants? Please, welcome to all of you. If you want to ask a question regarding to building in nature models, as Bob already doing presentation before.
May I, Pak Bambang?
Yeah, Bu Yuni, please.
Okay, thank you, Bob. You give us a very nice presentation because you explain in detail the explanation on the model. So if I'm not mistaken, you seem that you said the result can be seen in the next 5 to 7 years. Is it correct?
Sorry, can you repeat the question? You were saying 5 to 7 years of what?
Okay, sorry, if I'm not a mistake, you said that the result of your model, an example, you did the simulation that in the map, maybe your simulation will be seen or will be success in 5 to 7 years. Is it correct? Or maybe
yes.
a mistake. So
yes.
Okay. So if yes, did you still monitoring about the current condition, or does the current condition are still in the according with your simulation?
I'm sorry, I missed the last part of your question.
Okay,
I think
sorry.
the connection is a...
Okay, sorry. Does it seem if the current condition are still in according with your simulation?
Okay, yes, I understand your question now. So the current conditions, well, I'm not 100% sure about the current conditions to date. When we ended the project, this was in 2018, we were still monitoring also the conditions, and we were still checking with what was going on. And it seemed at the end of this study, around 2018, it seemed to still be in line, although there were some new findings that would change maybe the way we have simulated this. So it would update with more information, more data. So we may do things slightly different now. For example, we did see some changes of the bed levels outside of this monsoon season. So when we were setting up the model, we were assuming the main changes will happen only during those few months when the monsoon is at its peak, the northwest monsoon. But in reality, we see in measurements that there are also some bed changes going on outside of that season. So in hindsight, if I would do it again now, I would take the full year, which means that you would have much longer computation times, but you would have to accept that to be able to do it, to improve your model, let's say. And so with that, maybe the conditions are slightly different. I'm not 100% sure. And especially about the last 2-3 years, I'm not sure because I didn't look at the data, so I don't know what the current conditions are. But what I have seen is that the land subsidence has been really bad, and that there has been quite a lot of flooding there. So that has really been heartbreaking to see, and I hope it will improve. But I have some serious doubts there.
Okay, thank you, folks.
Okay, is there any question from other participants? Okay, Bob, still we are waiting for other question from other participants. Once of in your slide, you show us about the correlation between wave height and also CDF. The CDF means is cumulative density function.
Indeed, yes, sorry, I should have explained. That's indeed the cumulative density function.
Okay. And then if I'm not mistaken, you just show us in the middle of validation. How about in the upper of that validation? Because you don't have any data for that density function, or?
Yes, so basically this is a choice you make. When you're modeling, you can put the boundary conditions, and we put based on measurements and data collected, we decided to put offshore wave heights. But then if you measure, so this is what's on the outside of my model domain. But if you then look in the middle of the model domain or somewhere close to the coast, and you check is the value what we expected it to be, then we see that we are a bit lower than we had expected it to be. So maybe that's because the outside values are not correct. Maybe there have been some serious storms that are larger than what we put in. But it could also be that our model doesn't have the wave transformation and dissipation without the domain exactly right. So maybe we should have put slightly larger values in.
Okay. Okay, once again, if you still have any questions, Shibab, please. Amar? Yeah, Amar. Oh, yeah, please.
Yeah. Hi, Bob. I have a question for you for how you about the simulating the model using the 3D flexible maps. In one of your input, you put the sea level rise data. Is that correct? Yes. How do you do that in the model? Are you preparing the data and then you sum up with the tidal data, or you do that in the model itself?
Thank you for your question. I do that in the model myself, or in the model itself. So what I do is I impose two boundaries for the water level. So one is the tidal water level boundary, and then I add a linear increase component. So basically I have two separate boundary conditions, and at the inputs I can say sum them together. So I add on to the tidal variation, I add a linear increase, and then together they become this linear increase with the cyclic component. The model can do that.
Okay, thank you.
Okay, once again, is there any question from other participants? No question anymore? Okay, if there is no any question anymore, because we have to close the session is at 7. And then, as I already mentioned before, that today is the last meeting of our workshop. So next, okay, once again, thanks you, Bob, for your presentation. And then I would like to invite the head departments of Water Resources Engineering to giving the closing remark. Dr. Usi Andayati, time is yours.
Thank you, Mr. Bambang. The Honorable Mr. Volker and Mr. Bob, all as distinguished participants at this international workshop. Assalamualaikum warahmatullahi wabarakatuh, and good evening.
Suaranya Bu Usi kecil ya?
Sekarang sudah bisa.
Masih kecil, Bu.
Kecil, Bu.
Halo, ya? Bisa
Masih
dengar?
kecil Bu sih, nggak kedengaran.
Kalau begini?
Masih kecil Bu sih.
Oh, sure. Kenapa?
Mungkin outputnya puisi yang kecil.
Masih kecil?
I think good, Busi. Busi can continue closing speech.
Okay. Thank you. Assalamualaikum warahmatullahi wabarakatuh and good evening. Our precious time flies like an arrow, and we are getting to the closing time of our training workshop. At the end of this workshop, I'd like to say many thank you for your all kindness and effort to participate in this workshop and getting along with the touch training with the touch schedule. This workshop has generated a wealth of information and experience over 5 days of meetings. We were able to talk about how to implement the building with nature approach in a coastal, river, and other projects. We are now able to apply what we learned in the workshop to a real-world problem since we have gained new and useful knowledge. Building with nature is based on the science, technology, and society triangle. These three are constantly interacting with one another. Natural science are required to compare how ecosystem, physical and biological work, while social science are required to compare how public decision-making work and what encourages its participants. Technology is required to make things happen in smooth, efficient, and appropriate way. And society is the greatest stakeholder in all activities, supporting as a platform for setting and standard and making the decision. We ensure that building with nature alternatives is seriously considered in the project development of river and or coastal protection through the presentation, discussion, and input from experts from Deltares, the UDELF, and with events during the 5 meetings of the workshop. Nevertheless, we must remember that sometimes the extreme event is beyond the capacities and capabilities of a country to deal with. In concluding my remarks, I would like to thank all of you once again for your engagement. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dr. Usianda Yawanti, for the closing speech. Before end of this session, please make it your camera on so we can make a group pictures. Okay. Okay, 1, 2, 3. Okay. Okay, once again, thank you very much, especially for Bob Smith, for your nice presentations, and then for your time also. And then thank you very much for all participants in yours, for your active participation for the last workshop in building with nature, part of PKKM program 2021. And then see you next time.